Hi everyone. In today's video, we're going to continue our discussion on aromatic compounds. This time, we're going to finally delve really deeply into reactions that involve specifically the benzene ring. And the major reaction here is going to be your electrophilic aromatic substitution. By the end of this video, it's my hope that you'll be able to predict the products, propose reagents, and propose reasonable mechanisms for electrophilic aromatic substitutions to benzene. You would also be able to incorporate some reduction chemistry post electrophilic aromatic substitutions for efficient installation of some primary alkyl groups and as well as amino groups to benzene. Okay, so we've established that benzene rings are fairly stable and they typically do not just react on the go with several reagents. So, for example, we talked about how cyclohexene, while that can go through a bromination reaction to form your vinyl dibromide, benzene will not simply go through a bromination reaction if we treat that benzene in the presence of bromine. Benzene, however, will undergo what we call an electrophilic aromatic substitution reaction in the presence of a very strong electrophile. So here is a general scheme for an electrophilic aromatic substitution. You take your benzene, you react that with a strong electrophile that we're going to call E+, and then somewhere in that flask, a base will then be needed at some point during the reaction to then essentially replace one of the hydrogens in the benzene with the electrophile that you've added in your as your reagent. The general mechanism for electrophilic aromatic substitution is once you do form a strong electrophile, the benzene can then attack the electrophile in the nucleophilic attack mechanism, which will form this resonance stabilized cation, which gives the ortho and para positions on this particular cation a positive charge character. This is a very important intermediate in your electrophilic aromatic substitutions, and you will pretty much always see this intermediate. This is called a sigma complex, and the sigma complex is known as the resonance stabilized arenium ion. So the arene ring, it's forming an arenium ion that's resonance stabilized. And then the base in the flask can then come in and engage in a proton transfer with the proton on the same carbon as your electrophile that you just added to the ring. And in an E1-like mechanism, you can then reform your aromatic compound. And that's it. So that's the general mechanism. And pretty much all the reactions we're going to learn in this video are going to go through this very similar mechanism. And the driving force for that second step, where you go from the sigma complex down to your substituted product, is essentially the restoration of aromaticity or aromatic stabilization. This reaction is relatively robust in the sense that a wide variety of electrophiles can actually be substituted on your benzene. So you can take your benzene from the very middle and you can treat that with bromine in the presence of iron 3 bromide, and you would actually form your brominated benzene. You take a chloride, this time you treat it with an aluminum chloride, and that will get you to your chlorinated product. You can take an alkyl chloride, and once again, in the presence of an aluminum chloride, you would form your alkylated benzene. You can also take a acid chloride, so a carbonyl group with a chlorine as one of the substituents in the carbonyl group. In the presence of aluminum chloride, you would add a ketone to your benzene. So once you look at in the first four reactions on the left, notice that in all of these reactions, you have your electrophile, but you also have a pretty strong Lewis acid present. Iron 3 bromide and aluminum chloride are considered Lewis acids that would help to activate your molecule, your electrophile, to make it even more electrophilic in this particular reaction. The last two, you can take your benzene and treat it with what we call a fuming sulfuric acid, and that would put your sulfonate group on your benzene or your SO3H group in your benzene. And then lastly, take your HNO3, a concentrated nitric acid solution in the presence of H2SO4, and that will put a nitro group on your benzene. And like you said, for all these reactions, you either need a strong Lewis acid, and now in this case, in the last two cases, you can use a strong Bronsted acid, and these acids are required to generate the necessarily strong electrophile in order to break the aromaticity in that first step of your electrophilic aromatic substitution reaction. So now what we're essentially going to do is look at all of these reactions individually and just look at essentially the general trends. How do we generate the electrophile that'll be really strong? And then we're going to just revisit the electrophilic aromatic substitution mechanism. And you're going to see that the pattern is going to be completely the same for all of these different reactions. Okay, let's begin with the bromination reaction. So you can go through an electrophilic aromatic bromination of a benzene. If you treat that benzene with bromine in the presence of iron 3 bromide, one of the hydrogens on the benzene will be substituted off with a bromine atom. So the first thing we're going to look at is how is the electrophile created? How is that strong electrophile created in this particular reaction? So we've learned in the past that bromine is fairly polarizable. In other words, the electron density in bromine could really be redistributed in such a way that one of the bromine atoms could be fairly partially positive, and then the other bromine atom could be fairly partially negative. But we can absolutely induce a much more polarized bromine by treating with an iron 3 bromide. Iron 3 bromide is a good Lewis acid, so in the presence of bromine, your bromine is going to nucleophilically attack the iron 3 bromide to form this zwitterionic complex where now the bromine is complexed into the iron and you form a zwitterion, okay? This zwitterionic complex essentially is your strong electrophile. You've created a really strong electrophile, which is actually that red bromine, but let's use an equilibrium to showcase why this is a strong electrophile at this point. That red bromine could be dissociated from the iron complex in such a way that a bromine plus does get released into the flask. So you can think about this zwitterionic complex as really just a combination of a cation, a bromine cation, and the ion complex as your anion. Okay, so now you formed a really strong um, electrophilic reagent, which is essentially your halonium ion. Now the benzene can react with that strong electrophile in your electrophilic aromatic substitution reaction. So this will begin with a nucleophilic attack by your benzene on that strong electrophile in concert with the loss of a leaving group. So this is sort of like an SN2 reaction. And you will form the sigma complex as we've seen in the previous scene, which places a cationic character on the ortho and the para carbons with respect to the electrophile you just added. In this case, the electrophile is your bromine. But once you do form this, you then can have your base in the solution deprotonate that sigma complex to restore aromaticity. And the base in this particular flask is your FeBr4 minus. Notice that the arrows start from the bond between the iron and the bromine. The bromine is going to leave the iron complex and be used as a base. You would deprotonate the sigma complex, the CH bond breaks, and the electrons move over to form a pi bond in the ring to restore aromaticity. And you get your brominated benzene, or your bromobenzene, if you will. Okay, so that's the reaction, fairly straightforward. Once you had to create the strong electrophile, then you go through a substitution and you get your product. Okay, so the next one we're going to look at is the chlorination. As you can probably tell, this reaction is probably incredibly similar to the bromination. The only difference is your Lewis acid instead of the iron 3 bromide. We use aluminum chloride for this particular reaction. Virtually identical to your bromination reaction. The first sequence is your creation of your strong electrophile. Once again, your chlorine is polarizable. It can attack the Lewis acid like the aluminum. You will form your zwitterionic complex, which is indeed your strong electrophile in the flask. And this can be absolutely shown if you see the equilibrium between the zwitterionic complex and its dissociation to its cationic and anionic forms. You can see that a chlorine plus essentially exists within that zwitterionic complex. Once you do form your strong electrophile, your benzene can then come in and nucleophilically attack that strong electrophile in a nucleophilic attack, loss of a leaving group. Once again, to form your sigma complex that puts the cationic character at the ortho and the para position with respect to the incoming electrophile, where the chlorine has essentially ended up on the ring. Now, a base in the solution will then come in and deprotonate your sigma complex and then restore aromaticity. Very similar, if not pretty much virtually identical to your bromine case. Your base is your AlCl4 minus that you can start, once again, you start from the AlCl bond, you attack the sigma complex proton that is bound to the same carbon that also has the chlorine, and then in an E1-like reaction, you then deprotonate and then you restore the pi bond and restore aromaticity in your compound, and you form your chlorobenzene. So that's it. So the bromination and the chlorination reactions are very similar, if not pretty much identical. The only difference here is that instead of using FeBr3, we use AlCl3. So next up, we have the alkylation chemistry where we can take an alkyl chloride in the presence of an aluminum chloride, and we can actually essentially do an electrophilic aromatic substitution where we substitute out the hydrogen on the benzene with the alkyl group on that benzene. And we call this particular type of reaction a Friedel-Crafts Alkylation. So it's important you remember that name. Friedel-Crafts Alkylation is essentially an electrophilic aromatic alkylation reaction. So here's an example. We take your benzene, you react that with 2-chlorobutane in the presence of aluminum chloride. You essentially add the butyl group onto that benzene at the same position in which that chlorine existed. So the creation of the strong electrophile is only very slightly different to what we've seen with the chlorine and the bromine case. Very similar to the chlorine and the bromine case, the lone pair of the chlorine can actually attack the aluminum chloride, given that the aluminum chloride is a pretty strong Lewis acid. So you have that one lone pair attacking the aluminum. And then once again, you form this zwitterionic complex in which you have your set of aluminum that has a negative charge and a chloride a positive charge. And as we've seen in the past, you can imagine an equilibrium can form here in which that alkyl group is essentially dissociated from the aluminum complex to form a secondary carbocation. And we already know secondary carbocations are very electrophilic and very Lewis acidic. So you can imagine that this is essentially a strong electrophile in the reaction. So you have your secondary carbocation that can then engage in the electrophilic aromatic substitution reaction, all right, which you can depict as your benzene nucleophilically attacking the carbocation. You form your sigma complex, which once again places carbocation character at the ortho and the para position with respect to that incoming electrophile, which indicates is your alkyl group. And then the base in the solution can then come in and deprotonate the sigma complex. And there you go. You form your alkylated product from this particular reaction. So once again, I really want to just see that all of these reactions that we've just learned so far are all a pattern. It's basically exactly the same pattern, just repeated with different types of electrophilic agents. But be careful with Friedel-Crafts alkylations, right? Friedel-Crafts alkylations essentially involve the formation of carbocations. And we've learned in the past that whenever you have carbocations, there is always a possibility of rearrangements. And this absolutely does come into play for Friedel-Crafts alkylations as well. So consider this reaction where we have benzene and we wish to treat that with our 1-chlorobutane in the presence of aluminum chloride. And maybe we're hoping to get the alkylated product in which a N-butane is essentially added to our benzene. But what we get actually is a mixture of two products, one in which you have your butane substituted at the primary carbon, as well, and then the next one we have your butane substituted at the secondary carbon. And this mixture you cannot possibly avoid. The only reason why we could expect a mixture here is that a rearrangement must have occurred in this particular reaction. And so we must consider this mechanism to see how this could potentially occur. So once again, we have your alkyl halide in the presence of your aluminum chloride. That can absolutely complex to form, in this case, your zwitterionic complex, where I can call it a primary carbocation electrophilic agent, if you will. But I've explicitly drawn out that secondary CH bond because, as you can probably guess, there is probably going to be a rearrangement in the form of a hydride shift. This hydride shift occurs in this particular manner, where that CH bond breaks, and the electrons that were used to form that bond move over to the carbon that is bonded to the chlorine. In your hydride shift, or you can call it a nucleophilic attack of that carbon, and a loss of a leaving group, which is the chlorine, to form another electrophilic agent, which would be your secondary carbocation in your flask. So both your primary carbocation electrophilic agents and your secondary carbocation are going to be present in your flask to some extent, and both of those will act as electrophiles in your electrophilic aromatic substitution reactions. And so now you may see how substituting with the primary carbocation electrophilic reagent, you would form your product 1 or your product A, and then substituting with your secondary carbocation electrophilic reagent, you will form your product 2. So you can see how both of these, once if a rearrangement could occur, it will occur, but you would also get a mixture of products in terms that both of these particular electrophiles will be present to some substantial amount, and they would form a different type, all the different kinds of products that you can form. But however, this actually does introduce a synthetic challenge for us, because what if we did want to form product 1 or product A without any kind of rearrangement at all from occurring? How would we actually achieve this? Well, we would have to go through an alternate route in our synthesis so we can avoid the formation of a carbocation and then avoid our rearrangements as we move along the mechanism. So let's move on to the next part type of electrophilic aromatic substitution, and I will show you now a new method of getting this particular reaction or the synthesis to be performed in an efficient manner. Okay, so the fourth reaction is our acylation reaction, or the addition of our acyl chloride on our benzene to form ketone substituted benzenes. So the first step is the creation of the strong electrophile. This should now pretty much be old news to you. Once again, that acyl chloride has a chlorine with a lone pair that can absolutely attach to the aluminum, which then gives you a zwitterionic aluminum complex. This zwitterionic aluminum complex can be better thought of as dissociation into its cation and anionic form, which then gives you this rather unusual cation, a cation on an sp2 carbon, which is fairly unstable, but it is resonance stabilized. And this is the resulting resonance form that you can draw. This ion is called an Acylium ion, and that is the strong electrophilic reagent that is actually in a flask when you're trying to react this benzene in this particular reaction. And the aluminum AlCl4 minus is actually going to be your base as you keep moving through the reaction. So now let's look at the substitution portion of your electrophilic aromatic reaction. So starting with your benzene and then your Acylium ion. Your benzene can nucleophilically attack this incredibly electrophilic Acylium ion at the carbon, and then one of the pi bonds would have to break and then move over to the oxygen, which then gives you, once again, your sigma complex, where now you've added that Acylium ion at the carbon onto that benzene, and then the carbocation character now exists at the ortho and the para position with respect to that electrophile that you just added. So this is now back to your square one, good old electrophilic aromatic substitution mechanistic scheme. And then once you get to this point, then the base can then come in and deprotonate that sigma complex. Once again, your base now is your AlCl4, which then affords you your substituted product with your ketone, essentially, your carbonyl substituent on your ring. Let me now introduce a new reaction here, that, which would be very important to answer the question that we posed in the previous scene on how we can install primary alkyl groups on our benzene ring. So this is called a Clemmensen reduction. So you can take your alkylphenone product that we just formed, and you can treat that with zinc in mercury in the presence of HCl and heat. And so this will completely lop off that oxygen and then replace it with 2 hydrogens at that benzenic position. So that's an important reaction, because now what we can do is we can take this reaction again where we wanted to install that primary alkyl group without any rearrangement, and we can do so. We can first treat the benzene with our acid chloride of the same carbon chain length that we do want to install at the very end, and in the presence of aluminum chloride that would help us form that Acylium ion. And then when we do install that acyl group on our benzene, we can then completely lop off that carbonyl oxygen with zinc and mercury, HCl, and heat. And that would end up giving us our primary alkyl substituted benzene on our ring, which is great, which is exactly how we do this, and it will happen in really high yields. Okay, and then we're going to cap this video off with the reactions that involve the Bronson acid. So we start with the sulfonation reaction where we take our benzene, react that with fuming H2SO4. We would end up with our sulfonate group on our benzene ring in pretty high yields. And the key thing to note here for the creation of the strong electrophile is that fuming H2SO4 is actually equivalent to H2SO4, so the actual compound that we know, plus your sulfur trioxide gas, SO3 gas. That is an incredibly reactive molecule. It is really electrophilic, and it will absolutely react to your benzene fairly readily. Also, this reaction also generates water, and this reaction is done, it's sort of in water as well. And so water becomes our strongest base in that solution. Okay, so we have our benzene in our substitution reaction that's going to react with that SO3, that sulfur trioxide. The benzene will attack the sulfur, and then one of the pi bonds to an oxygen will then break and move over to that oxygen, which would then form your sigma complex that puts the carbocation character at the ortho and the para positions of that ring. Okay? And then you will end up with, once again, a base that can then come in and deprotonate your sigma complex to restore aromaticity. The strongest base in this flask, hands down, is water. Water comes in, deprotonates your sigma complex, and you form your sulfonylated benzene. Note that it is still in its basic form, but we also have H2O plus in the solution, and so that will then come in and protonate your product to form your sulfonylated products. Okay, and that is really it for your sulfonation reaction. Okay, the last reaction we'll learn today in this video is your nitration reaction. So you take your benzene, you treat that with nitric acid in the presence of sulfuric acid, and then you essentially place a nitro group or your NO2 on a benzene. Okay, so the first thing we're going to worry about, once again, is the creation of your strong electrophile. So HNO3 is already a strong acid, but it's not as strong as H2SO4. So in the presence of H2SO4, HNO3 can actually act as a base, which is very unusual, and deprotonate H2SO4, which will form this highly charged complex. As you can probably tell from this complex, we're dealing with a really unstable molecule. This will decompose to form this nitronium ion. It is this nitronium ion that is your strong electrophilic reagent. The loss of water in this particular last mechanistic step is the driving force to form that nitronium ion in the solution. But once you do form the nitronium ion, then you can go through your substitution reaction, which would of course launch us off first with our benzene reacting with our nitronium ion. So once again, form your sigma complex. And I know I'm saying this over and over again, but it's important that you hear this over and over again. In our sigma complex, the electrophile that you've added is going to place carbocation character at the ortho and the para position in respect to that electrophile. And then once we get to our sigma complex, the strongest base, in this case water, which is present in this reaction, will come in and deprotonate your sigma complex. Okay, so that's how you do your nitration reaction essentially, your HNO3 H2SO4, and you form your nitrated product. Another cool reaction that you can stem off of your nitration reaction is a reduction of your nitro group into an amine. So you can take your nitrated product, your nitrobenzene, and you can react that with either iron or zinc solid dissolved in HCl, And that will essentially form an ammonium. So you're going to reduce your nitrogen from your NO2 to your NH3 plus. When you get here, because you're in acidic solution, it will stay protonated. So in order to get to your neutral aniline, you can take that product and react that with sodium hydroxide. So this is two synthetic steps. The first step is in an acidic solution, iron in HCl or zinc in HCl. And then second step is just sodium hydroxide that would then deprotonate that proton ammonium. So that's great. So now you can actually go from your nitrobenzene to your aniline in your reduction step, which means that putting it all together, synthesis of aniline directly from benzene can occur if you first treat that benzene with HNO3 and H2SO4, you form your nitrobenzene, and then you treat it with iron in HCl, which will give you ammonium, or your protonated aniline, and then you can deprotonate that with sodium hydroxide, and that will get you to your aniline. These reduction reactions are actually really important. So it's important that you know how to reduce these different compounds or these different benzene derivatives. So, okay, so we've gone through quite a bit of different reactions that we could do with benzene, namely the electrophilic aromatic substitutions, but there's six of them we've gone through. It's my hope that you'll be able to start predicting the products of these reactions, knowing how to draw the mechanisms. You can see the patterns of your electrophilic aromatic substitutions. Um, and then you could also incorporate those reduction chemistries post electrophilic aromatic substitutions to for efficient synthesis, right? So whether you want to form your primary alkylated benzene or you want to form aniline, you should know how to get there through electrophilic aromatic substitutions. Okay, thank you so much for watching this video, and I will see you in class.